So this video is going to introduce the idea of a series, which is going to be the focus of the entire rest of the chapter. So we begin with a sequence. So let's let AN be a sequence. And this is a definition here. An infinite series, or sometimes we just call it a series for short, is the following notation. Okay, so what does this mean? We're going to be using the sigma a lot in this section and actually in the whole chapter. Remember, this is a summation. You start with A1 and you add it all the way down, and so it looks like this. A1 plus A2 plus A3 plus, and you do this forever. Okay? So a sequence is just a list of numbers, but a series is when you add them all up. But remember, we are adding an infinite number of things up. So, does it make sense to talk about a series as if it were a real number? So the answer to this question is, it depends. Okay, we need to be very careful on how we define such a thing, okay? Because we haven't really I just told you to add an infinite number of things together, but that doesn't really make sense, so we need to make it precise. So here's how we make it precise. We need another definition. So definition. The nth partial sum of a series. So nth partial sum of a series is the sum of the first n terms of the series. Okay? So this makes sense, right? We know how to add a finite number of things together. So we refer to the nth partial sum by the symbol Sn. Okay? So again, this just means we add up that many things. So S1 would just be A1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3. Keep this pattern going. What would Sn be? You just add up the first n terms. Okay? Another definition for partial sum is we could write it this way. We need another letter for the index of notation, but it looks like this. Okay, this is how you would write adding up the first n terms. So what do we notice here? We notice that we could actually do this all day long, right? We could keep going, right? Add up the first 100 terms, the first 1,000 terms. So that in itself forms a sequence. So we can form a new sequence of partial sums. So the sequence looks like this. So that would just be, that's the sequence that we're talking about, okay? We know about sequences by the last section, and so now it makes sense that we can talk about the limit of this sequence, okay? So we're ready to write the definition then that we care about. A series is called a convergent series if the limit as n goes to infinity of Sn exists. Okay? So if the limit as n goes to infinity of Sn is equal to some s, we say that this series converges to S. So this is what it means for a series, or the series to converge to a number. Okay? So in other words, when you write that you're actually adding up an infinite number of things, this is really the same as sending to infinity how many terms you're adding. So that is what a series equals. Okay? Now, conversely, or let me just say one more thing. S is called the sum of the series. Okay, so a series, think of it as an infinite sum, and it converges to a number, or it equals a number, if the limit of the partial sums is equal to that. That's what this part means right here, the limit of the partial sums. Okay? Now remember, we are assuming here that this is finite, okay? Infinity never counts as a limit that something equals. Remember, infinity is a way for a limit not existing. So we need to write that down too. If the limit as n goes to infinity of Sn does not exist, then we call this series a divergent series. We also say that the series diverges. Okay? So I'm hoping it makes sense why we studied sequences in the last section. Okay? It's because a series is really a sequence of partial sums, right? These sums that you see here, okay, these are partial sums. So what we're really asking ourselves is, does that sum approach a number? That's what we're looking at. Does that sum approach a number? If yes, it converges, and if not, then it doesn't. Okay? So in general, if we are asked to study a series, I like to say study a series. We are being asked if a series converges or diverges. Okay. All right, so let's do a quick example here. So number 1, I want us to study the following series. 1 plus 2 plus 3 plus 4 plus... So we keep going and going and going and going. Okay. How would we write this series, by the way, as sigma notation? You can write it this way. Right? Because all we're doing is we're adding consecutive numbers. Okay, how do we actually figure this out? Well, let's look at the partial sums. What's S1? The first partial sum is just 1. The second partial sum is 1 plus 2, which is 3. The third partial sum is 1 plus 2 plus 3, which is 6. And does this seem to approach anything? I mean, each time we go, we're adding a bigger and bigger number. So does this have a limit? Well, we can probably guess that this is not going to have a limit, right? These sums are not approaching anything. How would you actually figure it out? Well, we need to figure out what Sn is. Okay? What is that? That's the nth partial sum. In other words, we're adding together the first n numbers. How do you add the first n numbers together? Well, Gauss, way back in the day when he was a child, a famous mathematician, he figured out the formula for this. And you guys, I believe, used it in Calculus 1 when you were talking about Riemann sums. But this is just n times n plus 1 over 2. And so when we do the limit of that partial sum, we could easily see that this limit is equal to infinity, right? Because the top is growing forever and ever. So what does this mean? This means that the series diverges. Okay, that means the series does not equal anything. Okay. Let's do another example. So number 2. Suppose we know that the sum of the first n terms of a series is as follows. Does it converge or diverge? Well, you just have to take the limit as n goes to infinity of Sn. In this problem, they actually gave us Sn because they didn't actually give us the sigma. They just straight up gave us the Sn. Okay, so we can actually just take this limit directly. So how do we solve a problem like this? Remember to divide by the largest power in the denominator. We end up with the limit as n goes to infinity of 2 over 3 plus 5 over n. And when you send this to infinity, that guy goes to 0. So this whole thing equals 2/3. So what does this mean? This means that the series converges to 2/3. Okay. So if a series converges, you actually know that it actually converges to a number. However, there is something I want to say. It is actually rare for that to be the case. Usually it is rare for us to know what a series converges to. So let's write this down. Usually, even if we know a series converges, we will not be able to determine what number it converges to. Why? Sn will be too difficult to obtain. Okay? So this is extremely important, okay? So let me back up a bit here to look at these last two examples. Here we knew Sn only because famous mathematician gave us this formula, right? Handed out of thin air because he figured it out. Or in this problem, this was just straight up given to you as a given. They told us what the Sn was. But usually you're not going to know Sn. Okay, usually a series is just going to be given to you in sigma notation, right? It's going to look like this. And you're not going to have a way to write down Sn. There's not going to be some nice formula. Okay, so I'm demonstrating a few things here just so we understand the concept, but in practice, we're not going to have Sn. So this means we're not actually going to be able to take this limit directly. Okay, so this whole chapter is going to be about developing a whole group of tests that we can use to determine whether a series converges or diverges, because Sn is so difficult to find. Okay? Now, having said that, there are two specific cases where we will be able to find Sn. Okay? So, let me write this down. There are two special types of series we will be able to find an exact convergent value for. Okay, so we're going to examine those types right now. Okay, so I need a definition first. So definition. We need to learn what a geometric series is. So a geometric series is a series in which, if you look at the ANs, this guy is a geometric sequence. Okay, so what does this mean? This means that every geometric sequence looks like this. Okay, where A1 is a constant. R is also a constant. And just to remind you guys, in case it's been a while since you've seen the 11.1 video, this is called the ratio of the geometric series. Okay. So what we need to do is actually determine whether or not this series converges. So as an example, the following, before I do the actual proof here, let me write down some examples of a geometric series. So an example of a geometric series would be something like, we could do 1 plus a half plus a fourth plus an eighth plus 1/16. This is an example of a geometric series. Notice it's different from a sequence, right? A geometric sequence from the last section, we weren't adding them together, we just had commas, but now we're actually adding them all together. So there's a number like this, or there's a number like this, 3 plus, let's say 12 plus 48 plus 192 plus, these are both geometric sequences. Here in this one, A1 is 1, and the ratio is a half, right? Because we're multiplying each number by a half to get the next one. Here, A1 is 3, and R is equal to 4, okay? So, question. Which geometric series converge or diverge? Okay, I mean, if we come back here to these two examples, these are very different, right? Because in this first guy right here, we're adding smaller and smaller numbers to it, right? But here we're adding bigger and bigger numbers to it. So we already suspect that whether or not these things converge is going to have to do with what the ratio is. Certainly if the ratio is bigger than 1, then that means the numbers get bigger and bigger. And if the ratio is smaller than 1, the numbers get smaller and smaller. But that's kind of a clue to what happens, but we're not sure when it converges, when it diverges. So what we need to determine now is what types of geometric series converge and which ones diverge. So let's study this, okay? So we have the following. Here's our geometric series. And remember, these look like this. A geometric series looks like this, A1 R to the n minus 1. Okay? So let's look at case 1. Case 1 is if r is equal to 1. If the ratio is equal to 1, then this means that our series actually becomes just the same number added together over and over, doesn't it? It looks like this. A1 plus A1 plus A1 plus A1. We just keep adding the same number forever. Can that possibly converge? I mean, it should be obvious that it does not, right? This is impossible because as long as you keep adding something to something and it's the same number, then there's no reason why this should. But we can actually do this directly. Okay, what is Sn equal to? Sn is, remember, you just add the first n terms together. In this case, you're adding n times a1, right? Because that's what repeated addition is. You're adding the same number to itself n times. So, what's the limit as n goes to infinity of n times a1? It's just infinity. This means that, let me call this guy S. This means that, I'm sorry. I shouldn't do that. We are using that for something else. This means that the series diverges. Okay, so case 1, if the ratio is 1, then the series diverges. Let's do case 2. Suppose that r is not 1. Okay. I want us to look at the following series. Or not for the following series, but I want us to look at the partial sums here. Okay. We have Sn is equal to a1 plus a1 times r plus a1 times r squared plus, and you go all the way down to a1 times r to the n minus 1. Okay, so this is the sum of the first n terms. So here is the trick that we're going to use to find a formula for Sn. Remember I said that Gauss was very clever and he was able to find a formula for adding n numbers together when they're consecutive. This is going to be a similar trick. So here's the trick. We're going to multiply this entire equation by r. Okay? When we multiply the whole equation by r, we get as follows. Okay? We get a1 times r plus a1 times r squared plus a1r to the n minus 1 plus a1r to the n. So I multiplied everything above by r, but I also shifted it to the right. There is a reason for this. It's because I'm about to subtract the two equations together, and I want you to see what happens. Okay? On the left side, we have Sn minus Sn times r. And on the right, when you subtract, everything goes away except for the first term and the last term. You end up with a1 minus a1r to the n. So this implies what? So the left side, I could factor the Sn out and I'm left with 1 minus r. And on the right side, I could factor the a1 out. And I have left 1 minus r to the n. Okay. Finally, I'm allowed to divide by 1 minus r. We're going to divide both sides by 1 minus r. By the way, we should be careful here. We should be careful because 1 minus r, is it possible for it to be 0? No, because r is not 1. Remember, we're assuming that r is not 1 for this case, and so that's why we're allowed to divide by this. So this is what Sn equals. Sn is equal to, if I distribute this, it looks like this. A1 over 1 minus r, and then minus A1 r to the n over 1 minus r. Okay. So let's look at this limit right here, or this term right here, okay? This term, I'm going to keep the minus sign there. What I'm actually going to do is I'm going to divide this by r to the n. Okay? So what do we end up with? So it looks something like this, okay? So if we do the limit as n goes to infinity of what this looks like, if we do that, we have an issue here. This goes to 0 and this goes to 0, so that trick does not work. Okay, so here's what we're going to do. We're going to look at this on the next page. Again, we are examining this term right here. This is the one that we care about. Okay, so let's see. Let's write that down on the next page. We're doing the limit as n goes to infinity of a1 r to the n over 1 minus r. Okay, now what if r is less than 1? So what if r is between -1 and 1? Then what does this limit equal? This limit actually equals 0. Why? Because this right here, if you take a number between -1 and 1 and you raise it to a power, then this term is going to go to 0, right? Because when you take a number that's smaller than 1 and you raise it to a power, it starts to approach 0, gets closer and closer, right? So that's equal to 0. Okay, what does that mean? Okay, so this implies the following. The limit as n goes to infinity of Sn is equal to what? So if we go back, if this entire thing here goes to 0, then we just get this as our limit. So this is equal to a1 over 1 minus r. Okay, so we need to remember that. That's true in this case. Okay. What about if r is bigger than 1? If r is bigger than 1, then the limit as n goes to infinity of a1 r to the n over 1 minus r. If r is bigger than 1, then raising this guy to the nth power makes it bigger and bigger. In other words, this equals infinity. And if r is less than 1, we get the limit as n goes to infinity of, less than -1 is the last case. What happens here? Well, same idea, right? Not only does the number get larger and larger, but depending on n, it may be a positive infinity or a negative infinity. In other words, this limit does not exist. So what did we figure out? This is the only case where we got something that converged, right? Everything else, this is divergent, this is divergent. and r equals 1 was divergent. I guess we have one more case. What about r equals -1? Well, if you look at the original series, if r is equal to -1, then we have this, a1 minus a1 plus a1 minus a1, and so on. This must diverge, right? Because it keeps bouncing between a1 and 0, right? a1 minus a1 is 0, plus a1 is a1. Doesn't approach anything. And so the only time we approach something was when r was between -1 and 1. Okay, so this leads us to the following result. So for a geometric series it converges. Not only does it converge, but it converges to a1 over 1 minus r if r is between -1 and 1, and diverges for all other values of r. Okay, so this is the important thing that needs to be remembered for geometric series, okay? That it converges to a1 over 1 minus r if this is true. And by the way, another way to write this is the same as the absolute value of r is less than 1. So a lot of times you will see it written that way. Okay? All right. So let's go ahead and do some examples for geometric series. So number 3. So I want us to study the series 11 minus 11 over 5 plus 11 over 25 minus 11 over 625 So is this a geometric series? So notice the series is geometric. How can we tell? Well, what do we need to multiply each term by to get to the next term? Do you notice that to get from here to here, for example, we're multiplying by -1/5? And that's actually true for all of these terms, okay? So the series is geometric. And let's go ahead and write down that a1 is 11. That's the first term. And r is equal to -1/5. What about the absolute value of r? It's 1/5, which is smaller than 1. And remember, this is the condition, right? This is the condition that we're checking. So as we see up here, right? As we see right up here, if the absolute value of r is less than 1, then that means the series converges. So the series converges to a1 over 1 minus r. That's 11 over 1 minus -1/5, which is 11 over 6/5, which is 55 over 6. So it converges, and it converges to this number. Which simply means that if you were to add these terms forever and ever, the terms would approach 55 over 6. And remember, this is as a limit, so this means it gets as close as we want. The longer you do it, the closer you get. Okay, let's try another one. Does the following series (2 to the 2n, 3 to the 1 minus n) converge or diverge? Now, it's hard to say whether this thing converges or diverges just based on looking at it, right? Because of the way that it's set up. Now, there are a couple of ways of doing this, but what I would like to do is to just try writing down a few of these terms so that we can see the pattern. Because we do see n's up here, and when you do see n's up as an exponent, it means it probably is geometric. We just need to make sure we write it the correct way. Okay? So let's go ahead and figure out what the terms are. So what would A1 be? First term. If you plug in n equals 1, you get 4 times 1. That's just 4. What's A2? Plug in n equals 2. We get 2 to the 4th times 3 to the negative 1, which is 16/3. What's A3? 2 to the 6th power, 3 to the negative 2. This is 64/9. Is this geometric? Yes, we're multiplying each term by 4/3, right? To get here, times 4/3. Okay? So what does this mean? Well, the absolute value of r, so first of all, r is equal to 4/3. So the absolute value of r is 4/3, which is bigger than 1. What does this mean? So this is, let me be careful here. Let me first say that this is geometric. That's important. With A1 equal to 4 and r equal to 4/3. Since the absolute value of 4/3 is equal to 4/3, which is bigger than or equal to 1, the series diverges. Okay. So I want to show you guys a cool application for geometric series. So I always pose this as a riddle to all of my calculus classes when they first learn about a geometric series, and I ask, where have we seen geometric series before in real life? And in fact, you've actually known about these since you were a child. So where have we all seen geometric series before? Repeating decimals. Okay, so what do I mean by repeating decimals? Well, when you see a repeating decimal, for example, 0.3 with a bar over it, right? We know this is 0.333333333. This is really 3/10 plus 3/100 plus 3/1000 plus. And you could see that this is the pattern, right? And so this is really a geometric series. A1 is 3/10, and r is equal to, what do we multiply each term by to get to the next one? 1/10, right? So r is equal to 1/10. The absolute value of r is 1/10, which is less than 1. So it converges. What does that mean that this thing converges? Well, of course it converges. Otherwise, you wouldn't treat these like numbers, right? But we know that 0.33333 is a number. What does it converge to? Well, 0.3 with a bar converges to a1 over 1 minus r, which is 3/10 divided by 1 minus a tenth, which is 3/10 over 9/10, which is 3/10 times 10 over 9, which is 1/3. But you guys already knew that, didn't you? 1/3, if you put it in your calculator, is just 0.33333. So this goes to show, let me write something down. We can use ideas of geometric series to write any repeating decimal as a fraction, which is pretty cool. So let's do an example. I'll call this number 5. I want us to write 5.139, where 39 has a bar over it, as a fraction. So remember, this is really 5.1393939, and that pattern repeats forever. Okay, so how would we begin a problem like this? Well, the trick is to write it this way, okay? We're going to write this as 5.1 plus, and then we have 0.0393939 ... So let's throw the 5.1 off to the side, and we're just going to look at this for now, okay? We notice that that's 0.039 plus 0.00039 plus 0.0000039. So this is the pattern, and so this is a geometric series, isn't it? If we want to write it as fractions, we can. This is 39 over 1,000 plus 39 over 1, 0, 0, 0. We add 2 more zeros because each time we added 2 more zeros. Plus 39 over 1, 0, 0, 0, 0, 0, 0, 0. So what is A1? A1 is 39 over 1,000. And what's R? It's 1 over 100, right? Because each time we're multiplying by 1 over 100. So does this converge? Yes, it does, right? The absolute value of R is equal to 1 over 100, which is less than 1, so it converges. What does it converge to? A1 over 1 minus R. What's A1? Remember, the first term was 39 over 1,000. And then 1 minus R. This is equal to 39 over 1,000 over 99 over 100, which is 39 over 1,000 times 100 over 99. Let's just reduce this. This is 1, this is 10. And then if we use a different color, this is, if we take out a 3, this is 33, and this is 13. Sorry, that's a little unclear. I didn't know yellow would be so hard to see. This is 13, and this is 33. That's better. So what do we get? We get 13 over 330. Now, is that our answer? No, because remember, we took out a 5.1. Let's add a 5.1 to 13 over 330. 5.1 is 5 1/10, or 51 over 10. So it's really 51 over 10 plus 13 over 330. So we're going to get a common denominator here of 330. So I'm going to multiply this by 33 times 33. So if we work this out, this is what I get on my calculator. I get 1696 over 330. 1696, which reduces to 848 over 165. I guess only a 2 goes in. And this is our answer. In other words, I claim that 5.139 with a bar over it gives you 848 over 165. They're the same thing. And you could check that. If you do 848 divided by 165 in your scientific calculator, you will get 5.1393939. So pretty cool that we can use this method to write any repeating decimal as a fraction. Okay. All right, so this was just the first type. If you recall, we had 2 types of series where we could find the sum exactly. So let's do another definition here. A telescoping sum is a sum in which most terms cancel when writing out Sn, allowing us to take its limit. The idea is that if you take Sn and you write it with all of its terms, it's very, very big, right? You've got these dots, which corresponds to something really large. It's like a telescope in the sense, though, that when you have a telescoping sum, you're actually allowed to cancel all of the terms inside except for possibly the first and the last term, for example. And so then when you end up with just 2 terms or 3 terms or whatever it is, you could take their limit quite easily. Okay, so that's the trick behind telescoping sum. We're going to do an example so that we can demonstrate how telescoping sums work. So just as a tip, you may need to use partial fraction decomposition in order to see its telescoping nature. Okay, so make sure that you brush up on how to do partial fraction decomposition before you start looking at problems like this. So I'm going to do an example. This is going to be number 6. Show that this series converges. And find its sum. Now, it is not easy to look at this sum just on its own, but here is the trick, okay? The trick is to take this term, 2 over n times n plus 2, and use partial fraction decomposition on it. So we know, because the bottom is already factored for us, that this is equal to a over n plus b over n plus 2. So this is what we need to find. What is that a and b equal to? So I'm going to multiply by the LCD. I'm going to multiply this whole thing by n times n plus 2. This leaves me with 2 equals a times n plus 2 plus b times n. And as we know, we can plug in anything we want for n in order to speed things up. So if I plug in n equals 0, I end up with 2 equals 2a, which means that a is 1. And if I plug in n equals negative 2, then this gives me 2 equals negative 2b, which means that b is negative 1. Okay? So this means that my sum right here is really what? It's really one over n minus 1 over n plus 2. Right? Because that's what I showed. I showed that because a is 1 and a is negative 1, that means this is 1 and this is negative 1, okay? Now you're going to see that this is a telescoping sum, and here's how this works, okay? Because you have something minus something, it means that when we expand this, we hope to start to see cancellation. So I'm going to write out several terms here, okay? So let's start with Sn. Or I'm going to start with, let's start with S1. S1 is, now remember, our sum, I'm going to put it here for reference, is 1 over n minus 1 over n plus 2. So if I do S1, that's just 1 over 1 minus 1 over 3. If I do S2, this is 1 over 1 minus 1/3 plus, and then the second one is 1/2 minus 1/4. So far we don't see any cancellation. Let's keep going. How about S3? We get 1 over 1 minus 1/3 plus 1/2 minus 1/4 plus 1 cubed minus 1/5. We notice something. Do you guys see that the minus 1/3 cancels with the positive 1/3? So this is really cool. Let's see what happens if we keep going. What would S4 be? 1 over 1 minus 1/3 plus 1/2 minus 1/4 plus 1 cubed minus 1/5 plus 1/4 minus 1 over 6. What cancels? Well, the negative 1/3 and the positive 1/3 cancel. The negative 1/4 and the positive 1/4 cancel. So what were we left with? We were left with this guy, both positive, and this guy, both negative, and 4 terms canceled. Okay, I'm going to do another one. You do this many times until a pattern becomes very clear. So what cancels? The negative 1/3 cancels with the positive 1/3. The negative 1/4 cancels with the positive 1/4. The negative 1/5 cancels with the positive 1/5. And here's where we got a full cancellation of this middle term. Why did we get that? It's because here, this guy cancels with two terms in front, but then this guy, so the second term of each of these parentheses cancels with two terms in front, but then the first term cancels with two terms in the back. And so this guy made that guy cancel, and this guy made that guy cancel. So I'm hoping that we see a pattern here. This means that everything except these guys and these guys is always going to cancel, right? Because everything else is going to have something two terms in front and two terms in back in order to get rid of it. So we're ready now for the important one, Sn. We have 1 over 1 minus 1/3 plus 1/2 minus 1/4 plus, let me actually write down one more, 1/3 minus 1/5 plus, and what are the last three terms going to be? Well, the third to last one is going to be when we plug in n minus 2. So it's going to be 1 over n minus 2 minus 1 over n plus, and then 1 over n minus 1 minus 1 over n plus 1 plus 1 over n minus 1 over n plus 2. So this is what Sn looks like. This is the first n terms. But what cancels? Well, this cancels with 2 in front. This is going to cancel with stuff that's in the dots. Okay. What about the negative 1/5? Again, cancels with stuff that's in the dots, and so that's totally gone. And what happens over here? Well, this negative 1 over n cancels with this guy. So this guy cancels with 2 that's behind it. This guy's going to cancel with stuff that's 2 behind it. This guy's going to cancel with stuff that's 2 behind it. So the only thing that's going to remain, everything in the middle cancels. The only thing we're going to remain are these circled terms. That guy, and this negative guy, and this negative guy. So what we have shown is that this giant thing really, as like a telescope, we can actually shrink it down to the following. 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. So the limit as n goes to infinity of this is equal to, well, these two guys go to 0, don't they? So the limit as that sequence goes to infinity is 1 plus 1/2 is 3/2. Okay, so what we have just found is that this series, the sequence of partial sums, actually equals 3/2. So this is how we would write the answer. Let me go ahead and write it right here. The series converges to 3/2. This is how we write the answer. Okay, so this is a demonstration of a telescoping series. They're a little tricky to spot sometimes, but if you notice that the bottom can be factored, right? This is what, this was sort of our clue. When we notice that this bottom part here can be factored, then we know that it might be telescoping, and that's why we did the partial fraction decomposition and moved on from there. Okay. We are going to So we saw an example of a series that goes to, that converges to a number. We've seen some series that diverge, right? So far, everything that we've seen that diverges clearly diverges because the terms get arbitrarily large, right? The terms actually grow and grow. But I want to show you an example of a series where the terms are getting smaller and smaller. And we need to study whether or not this converges or diverges. So let's look at an important series. This is called the harmonic series. What is the harmonic series? It's 1 plus a half plus a third plus a fourth plus a fifth. We can see the pattern. In other words, this is equal to the series 1 over n. Now, this series is not, notice that this guy is not geometric, right? You do not get to the next term by multiplying a term by anything. So we cannot use any results that we know about geometric series to do this problem. So let's look at this series. Let's look at the first few terms, or the first few partial sums to see what's happening here. So first one is 1, okay. The second partial sum, if you add 1 plus a half, you get 3 halves. The next one, S3, is 1 plus a half plus a third, which is what? That's 6 over 6 plus 3 is 9 over 6, and it's 11 over 6. What's happening? Do these seem to be approaching anything? It's hard to say. They are getting bigger and bigger, but the terms themselves are getting smaller and smaller. So we're not sure, is this going to approach something or not? So here's what we're going to do. What we're going to do is we're actually going to look at powers of 2. Our first one is 1. Our second power of 2 is 3 halves. What would S4 be? Okay. So the trick is to realize that this guy right here, these two guys have to add up to be more than a half. How do we know that? Well, because 1/3 is bigger than a fourth, and a fourth plus a fourth is a half. So this guy has to be bigger than 1 plus 2 times a half, which is 2. Let's jump to S8, the 8th partial sum. Again, we're looking at powers of 2. We have 1 plus a half plus a third plus a fourth plus a fifth plus 1/6 plus 1/7 plus 1/8. I'm going to group these two together, and I'm going to group these two together. This is bigger than a half by the same reasoning as above, and this is also bigger than a half because all of these are bigger than an eighth, right? Well, the first three are. The last one is an eighth, but the point is 4 times an eighth is a half. So this whole thing is bigger than 1 plus 3 times a half, which is 2.5, right? Let me write that as 5 over 2. Now, I hope we see a pattern here. The second partial sum was bigger than 1 plus a half. The fourth partial sum was bigger than 1 plus 2 times a half. The eighth partial sum was bigger than 1 plus 3 times a half. So we notice that, yes, it takes twice as many terms each time, but what we notice is that the 2 to the nth partial sum is larger than 1 plus n times a half. So what would the limit as n goes to infinity of this guy be? Well, it's certainly going to be larger than the limit as n goes to infinity of 1 plus n times a half, which is infinity. In other words, these grow without bound. So this implies what? That the harmonic series diverges. Okay, so the harmonic series diverges. We are going to refer back to this a lot because this turns out is an important example that illustrates lots of different concepts that we're going to be learning. Okay? Now, we've talked a lot about definitions, and we've had some definitions, but we don't really have any interesting theorems yet, and that's where this next theorem comes in. Okay, so theorem. If the series converges, then the sequence converges to 0. Okay, so what does this mean for the sequence to converge to 0? This means that the limit as n goes to infinity of an is 0. Okay, so what this is saying is if our series converges, then the sequence itself converges to 0. Okay, so what is the proof of this fact? So I want us to suppose the series is equal to S. Okay, that's what it means to converge, right? And let's suppose that this guy is a real number. Okay? So what we need to do is now show what happens to this guy. So what is the limit as n goes to infinity of an? All right, well, any term, isn't it true that if we take any partial sum and we add the nth term to it, we get the nth partial sum, right? So if you take a partial sum and you add the very next term, then you get the next partial sum. What this means is that any term can be written as a difference of two partial sums. So this is true. But now I can do this. But each of these goes to S. Why? Because we're assuming that they converge to S. So this is really S minus S, which is just 0. And that's the end of our proof. Okay? So what does the theorem say? The theorem says that if this guy converges, then the limit as n goes to infinity of an is equal to 0. Now, does this mean that we have a way now to tell easily if something converges? So is the converse true? What does converse mean? So in other words, can I say that if the limit as n goes to infinity of an is 0, then this guy converges? Can I say this? The answer is no. For example, isn't it true that the limit as n goes to infinity of 1 over n, that's 0, but this series diverges? We just showed that in the last example. In other words, the converse is not true. This is not the case, okay? So be careful. So then why is this theorem useful? Well, the theorem is not useful to find a convergence sequence, but it is useful for finding one that diverges, okay? A restatement of the theorem gives us what we call the test for divergence. Or actually, let me call it the divergence test. And I'm capitalizing it because I want to this is a formal statement, a divergence test. The divergence test says the following. Now, we know from this theorem back here that if something converges, then its limit must be 0. So how can we use this fact? We could say the following. That means that if the terms don't go to 0, it must diverge. Okay? So if the limit as n goes to infinity of an is not 0, then the series diverges. Okay. This is extremely important. I'm going to put a big box around it. This is one of the big results of this section. I mean, we learned a lot of stuff in this section, but this is one of the big results. It's our first test. It's called the divergence test. And I will say something, just note, or rather, instead of a note, I'm just going to say, be careful if the limit as n goes to infinity of an is equal to 0, this test tells us nothing. In other words, use another test. Okay, so not every test gives us conclusive information. Okay? Let's do a quick example. So we're on number 7. We're going to study the following series. Three n cubed plus 2n squared over 5n cubed minus 3n. Quite complicated, this series, but we're just going to use the divergence test, okay? We're going to see if the terms go to 0. The limit as n goes to infinity of an, we're going to take the limit as n goes to infinity of 3n cubed plus 2n squared over 5n cubed minus 3n. So I'm going to divide by n cubed this is going to equal the limit as n goes to infinity of 3 plus 2 over n over 5 minus 3 over n squared. This goes to 0, this goes to 0, and so this whole limit is equal to 3/5. So what did we just show? Well, the divergence test says that if that limit is not 0, what happens? This implies that the series diverges. Okay, so we used the divergence test. So I should say by the divergence test. Okay, everything that we do in this chapter needs to be justified. Okay, we have to cite what test we're using. Okay, so let's figure out, or let me write down another couple of results in this chapter, or this section. I know this is a long video, I apologize, but it is a really long section, okay? So let me go over the following theorem. So I want us to say, let AN and BN be convergent series. A the first thing we could say is that if you multiply a series by a number, so I should say that let C be a real number, then if you take a series and you multiply it by a real number, this guy is convergent. Second part, if you add the two series together, it's convergent. And third part, if you subtract, it's also convergent. And not only can we say that, but we can even say what they converge to. CAN is actually going to equal C times whatever that series converges to. AN plus BN is going to equal the sum of the two series. And this is going to equal the difference. Okay, this is really nice when you have a series and you're not quite sure how to approach it, but you do notice that it's the sum or difference of two, series that you know how to approach individually. Okay, so let me do an example here. This is going to be number 8. Find the sum of the series if it converges. And the series is going to be these two. These two series look very, very different. Or sorry, this is one series. It's the sum of two fractions, but they look very, very different. They almost look incompatible. So what we're going to do is we're going to study these two pieces separately. So let's start by looking at this guy. Where have we seen this guy before? I'll give you a hint, okay? We actually did an example earlier of telescoping sums, or telescoping series. If you recall, by an earlier example, we actually got the following. We got that that's equal to 3/2, right? Now, how can we deal with this one? Well, by the theorem we just wrote down, isn't this the same? If I pull a 5 out, isn't this the same as 5 times this series that we did earlier? Why am I allowed to pull a 5 out? Again, it's by the theorem that we just wrote down, right? You look here, this is saying that we can pull a number, or sorry, right here, we can pull a number out, okay? So, what is this guy equal to? Well, we did the earlier example of 3/2, so this is really 5 times 3/2, which is 15/2. So cool, this guy converges. Now, what about this guy? Well, if you look at what this series is, it's 1/4 plus 1/16 plus 1/64 plus. We have not done this series yet. However, it's easy to tell that this is geometric. Okay, what is our ratio? Well, we're multiplying by 1/4 each time, right? So the absolute value of r, I guess I should say that r is equal to 1/4. The absolute value of r is 1/4, which is less than 1, which means that it converges. And what's a1? The first term is 1/4. Remember, it converges to a1 over 1 minus r, which is 1/4 over 1 minus a fourth, which is the same as 1/4 divided by 3/4, which is 1/3. So if we take this result and we take this result, this means that this guy converges to 15/2 plus 1/3, which is 47/6. So the theorem is nice because it allows us to take a complicated thing and split it up into two easy things. Now, it's worth pointing out that we were only able to do this because both of the series were converging to something, right? If one of them diverges, then you can't really say what would happen if you add the two together, okay? But this only works if they both converge. Okay. There is one last thing I want to say. This is just a useful tip. Useful tip when dealing with a series, okay? We're going to cite this a lot later on. This is why I want to say it, okay? A finite number of terms cannot affect whether or not a series diverges or converges. What does this mean? Well, this means, for example, remember we looked at this series. This guy diverges, right? What happens if I were to instead start at the 200th term? I mean, I'm taking away the first 200 terms. Does that mean that maybe now it converges? No, it still diverges. It doesn't matter how many terms you subtract away or add in, your series, the behavior will not change, because what's happening, what's causing it to converge or diverge has nothing to do with what happens at the beginning. It's what happens at the end, and what I mean by end is as we go to infinity. Okay, so I'm going to say the long run, in other words, limit at infinity, is what causes the behavior. So we are going to be using this fact quite a bit later on to justify some things. So that is the end of this lesson. The big takeaway from this lesson are the definitions. Make sure that you know what a series is. Make sure that you know how to deal with telescoping and geometric series, and then also understand that we have something called the divergence test now. And this is something that we're going to use in the future. So for the next several sections, what we're going to be doing is developing tests that help us determine whether or not a series converges or diverges. Thank you very much for watching, and see you in the next video.